My name is, as he said, Peter Karlsson from AP&T Denmark. I represent Denmark and UK for AP&T. With me I have Johan Friberg. As always, it's a late change, but even to the better, because Johan have been marketing manager for many years, and before that he was tooling manager for the tooling division in AP&T, so he knows a lot about tooling. First of all, I want to say thank you to organizers and Thomas for everything, inviting us here, especially to Mr. Poye. To be back again. Actually, we was here 10 years ago. I don't believe I've been 10 years older, but that's probably it. First, I just want to introduce AP&T for you. Johan will talk about the press hardening and the hot forming after my introduction of AP&T. We can wait. I love computers. Here we are. AP&T stands for Automation, Presses and Tooling. We are a Swedish company. We have 3 factories in Sweden where we produce all our machinery, automation, presses and tooling in Sweden. We did this strategic decision 10 years ago, 15 years ago, that we said we will only produce what we are good at. In the end of 90s, everyone was hunting everywhere to get customers, but year 2000 we decided to do automation, presses and tooling that we are good at, and today we can see this is a very good decision we did. Actually in 2010 we went from Premier League up to Championship, and that was good. All these things you can see here we did do in Sweden. This means that we keep the competence in-house. We have a model-based system. We follow our customers globally, and we have personal contact at all levels. And we are marketing leader in defined niches. We are one of the 5th biggest in the world for making automation, presses and tooling. But we are also market leader on defined niches. And one of these niches is, of course, the press hardening or the hot forming progress. We are worldwide. We have our own companies in China. That is very big today. We don't produce, only sell and service. Czech Republic, Denmark, Germany, Japan, Poland, Slovakia, Sweden, United Kingdom and USA. In the rest of the world we have, like you say, Belgium, Brazil and so on. We have agents, but all the production, as you can see, again, is in Sweden. We are actually building a new factory now in Ulricehamn. That will be 10,000 square meters under one roof, only for tooling and automation. And like I said, we are a market leader in defined niches, and one of these niches is press hardening. We have produced most line in worldwide, and this is a small reference list that we have done. I hope you will welcome Johan Friberg, because he will take over now, because now he will talk about technique. Thank you.
Okej. Är det en sån här också? A quick change. Yes, we have an agenda here for today. We have managed with this about AP&T. We have something about hot forming history, market trends and demands. That was what this presentation was about from the beginning, but I am a toolmaker, so I put in a lot of other stuffs also. We have something called AP&T line solution, something about the lines for hot forming. Peter mentioned hot forming is for AP&T 80-90% of the turnover today, and what we can see in the future it will be even more. Then we have something called die step by step. I will go quite brief into this die making here. And then we have some time left. You can ask me questions about this. Yeah, we start with the history. See, I have a screen here. I can use that one. Yeah, this material was developed in the middle of the 1900s by a company up in North Sweden. 73, it was this hot stamping process was developed, and 75, and the R&D project together with Volvo Truck. It was a big bumper part they produced. 84, have Saab Automobile, one of the first OEMs, put that in the car. It was side impact beams for this protections. And the bumper beam in US, 91. There was, it started there. And in the beginning it was more for the premium brands of the car. If there was a really big high premium car, they have some of this kind of parts. Today it's totally different. It's more or less a competition today to have more and more parts inside the car. What is press hardening? Yeah, it's a method to make products with ultra high strength steels, typically used in automotive sectors. And these side impact beams, as I mentioned before, front and rear bumpers, floor tunnels, B-pillars, chassis components, and rear axis. This is a one-step forming. You can do a really deep drawing operation in one operation. So this tunnel part, for example, 450 millimeters high, is no problem at all to make in one step forming here. The material we use is uncoated or coated, and the coating can be aluminium silicon, aluminium silicium, as you can see here. This is an uncoated part. It's a lot of scaling of this part if you don't do it in the right way. The aluminium silicium have some rust protection on the surface. There is always now coming something called zinc coated material, and what we can see now is that this will come more and more on the lower part of the car. Yeah, market trends, what have driven this so hard? Yeah, this picture show all these crash tests from the beginning here in 1990 to where we are now, 2012. All these crash tests has been stronger and stronger, higher demands for the car. So we need to have more strong parts, harder parts. But of course, if you have stronger parts, you can't increase the weight because that will have a poor impact for the fuel consumptions. So this is one way to do it, use press hardened material or aluminium or something else. I mentioned something about this crash performance. What happened in the last is this offset crash. You can see here we are 40% offsets. In the past, now we have a 25% offset. So this crash will, it will be more and more stability in the car to manage that. I have something you can see. I pick it up on the internet. You can see a Volvo car here, how it looks like for this kind of crashes. I mean, it's incredible, and you can see where the passenger are sitting. It's still pretty safe to sit inside there when the car looks like totally demolished after this. Yeah, you can see inside the car it looks quite safe. Even that it looks like it is here. One other thing who has drive this for this type of material is the current fleet in Europe today use in average 140 gram CO2 per kilometers, and today it's no penalty here. If the target of 95%, which is coming in 2020, not is fulfilled, there will be a penalty per car in 4,000 euros, and that will of course have quite a high impact to buy a car. And if you look even further, in 2025 this penalty will be even higher, and the demands are going down even more. So from the beginning it was not just the parts in the car for the crash performance. Now it's also to lower the weight of the car. And of course, if you can take a lot of parts, 3 millimeters thickness, and you can have hot forming, press hardening parts, you can more or less make it half the thickness, and that save a lot of weight. Market demands for the material. Yeah, we can see what's happening with the mild steel. This is more or less 2010 roundabout. You can see this is going down a little bit. Aluminium start from a low value here, going up a little bit here. But of course, this is a huge increase because compared to steel, aluminium weight is lower, and this is parts in the car. If you look at this hot forming material, this ultra high strength steel material, you can see we start from a low position here, and the trends are more or less up in the sky. There are of course other materials. You have composite and other things, and that will also increase a little bit, but that is more for the high premium cars. This is something we have got from ArcelorMittal. We have seminars around the world, and Arcelor is one of the speakers for that. And this is their prediction of their material. This is only for the aluminium silicium, this coated material. If you see where we are right now, the overall trends is increase really much. But they just calculate with the UC-bor. If you take boron steel, uncoated material plus zinc materials, will this be even higher? If we come back to Volvo cars again, in this famous V70 car they produced in 2000, it was 5-6 parts inside the car. It was bumper, B-pillars, door beams. And for each model they have increased it a little bit. So the benchmark more or less was around 15 to 20% this high grade steels inside the car. And now for the new platform, the new SPA platform they calculate with 40%, and that means approximately 40 parts inside the car. And this is really a new trend. And in our view, in Peter and my view, this is another slide showing more or less the same thing, but this is the demands you can see here, and the capacity of the press hardening production is here, so they are not on the same level. But of course, we can't see that the different are so much. I mean, the car manufacturer, they produce other type of material. They stay with the material they have, but this is the calculation everyone have. Some comparison. This is a study made by Fiat. We produce a couple of lines and tools for them as well. This is a B-pillar. It's produced as a cold form condition, and to get this stability and the crash performance, they have two parts which they weld together. So they need a lot of dies to produce this. The weight is of course quite significant. When they change this part to a hot form part, they have just one part, and they have something called patchwork. They spot weld this small blank here when they have two flat blanks, and then they heat it up and put it inside the tool and press it. So the savings for this one, if you piece price 25%, and that is more or less the kilo price for the material, because the cycle time, the production time for this is quite longer than cold forming, a little bit longer. Tooling, saving with 42%, because here we have one die making the forming. If you do these two parts in the cold forming operation, I think there are 3-4 dies per part, so that's quite a big saving. And the difference in kilo was 27%. So this is, of course, a huge benefit to put these parts inside the car instead. What we can see in the trends for the future is this is what we call a door ring. They can put 3-4 parts together, the tailor welded from the beginning in flat condition. They can have different type of material, UC bore or ducty bore or different thicknesses. So they can have really what they need for this crash performance. They can have different thickness everywhere, so they can match the crash test in the simulation with the reality. So this is also what we can see in the future. Something else they have is Taylor rolled blanks. It's a company in Europe producing that one. This is for different cars. You can see they have different thicknesses where they need to have it coming from the crash tests. So this is also a new trend, and of course this is also what we can see, and there is a weight savings for this as well. Yeah, tooling wise, soft zones is something we can see also. Yeah, this is quite complex inside the dies. You add in heating elements in the process. You can have softer areas in the material, and you can have hard areas on one side of this and soft on the other side. Of course, this is quite complicated inside the die with a lot of spring back problems in a process which is stable, and also hot cutting, also something you can do inside the dies. This is what we can see coming in the future. The process, if you come in on that. Yeah, we start with the material, which is approximately 600 megapascal. We heat it up in the furnace. We go from room temperature 20 Celsius roundabout. We go up to austenitis temperature around 900 Celsius. We put it in the die and we cool it down rapidly till we reach martensite. This is the total process. And in AP&T, we have two different ways to do it. You can have what we call a traditional press forming, hot forming line. And you can see you have automation on one side, so you can run continuously. You have a furnace, and this furnace is depending on the cycle time. The total cycle time of the line can be from 12 meters up to 100 meters. So, and then on the other side you have the press, and inside the press the important things, the dies. And of course everything have fans around, because we produce with really hot material. We have developed a solution in AP&T. We call it feeder furnace. Instead we have this long furnace here. We have furnace on top of each other. So we have 7 chambers on top of each other, and we have half the footprint compared to the other line. So this is something which is what we can see is for the future, and we are of course selling it right now. In an old traditional line, we can have, I don't know if this worked, should be film. maybe. Oops, it works, I think. We'll make a test here. Yeah. Depending on the length, of course, this guy needs to run really long way if it's a problem on the other side. So, but this was not why we developed this feeder furnace line. It was more some problem can occur when you put in the blank in one side. Then these blanks should be transported on rollers 80 meters and must be exactly on the same spot on the other side. That can be a problem also for the maintenance of this kind of rollers and equipment. We have what we call this feeder furnace, and I have some animation on that as well. Yeah, it starts. You can see we have the destacking here. We have left to right, in this case, B pillars on these beams. We make a center station, we make marking, and we measure the thickness of the material so we don't have double blank. Double blank is never good to have inside the dies. And you can see we have forks here taking care of the blanks. So where we have made the centering here, we have perfectly controlled and know exactly where this blank are during the whole process. Instead that we let it on these rollers, and that goes by rollers 80 meters. So here we have 100% control. When we developed this furnace, we call it pizza furnace because it's like a pizza spade taking these blanks and adding them inside the furnace. It doesn't matter if we take the blank from that position to the die, or if we take it from the closest to the die position. We have a program of this automation system, so we have always exactly the same time. So we have control over the temperature. One other benefit with this solution is something happens, some furnace is breaking down, you can disconnect them, and the program take care of everything. So you run with 20 furnaces instead of 21. So the cycle time will go down a little bit, but you can still produce. If you have some problems with this long line, you need to stop everything and wait 24 hours to have cool down. Then you can do your maintenance and start it up again. So this is more convenient. Yeah, I am also showing in reality, so we can see that we have it. As you can see, the port is red, it's 920 here, and when we close the die, the temperature is around 800, 840. So the environment for the die is of course not so good. The wear is much more here than in cold forming. The dies, yes. Yeah, I mentioned it before. This is one-step forming. There are some systems with where they make the pre-forming in cold condition with the full die sets, and then make the hot forming quenching in one operation. But this is just one company, and they are running some type of special material for it. We use it as a one-step forming, and you can see here when we have the material in cold condition, we are around 400 megapascal. We have an elongation around 20-22%. When we heat it up, we are more or less up to 50% elongation, and that is extremely good for deep drawing. Then when you fast cool it down to room temperature again, you have 5% elongation. This material is completely dead. You don't have any spring back. You don't have any problems. More or less the first stroke you're doing, if you design the die right, is inside the tolerances. And that is different compared to progressive dies and this kind of thing. So this is a much more safer process. Yeah, our process is more like just for cold forming. We use some kind of simulation programs. We have surface programs, we have cooling channels programs, and we have, the simulations takes around 30 minutes, and we do a lot of simulation, of course, to make all compensations for shrink and everything. But we have moved the most of the verifications, all things we have moved in the simulation program. So we can say that we have moved all the fine-tuning we have in the dice before. We have moved into in our simulation program, and that has helped really much for this. So we say we are approximately 60% in the simulation design process. So we simulate first for the formability, then we simulate for the cooling water flow and everything, so we know we have a full control over the process. Simulation, yeah. I don't know how the simulation program looks like for cold forming, but I think when we start the simulation for the hot forming, we have one elongation curves. Now, depending on how high this part are, we have lot of elongation, but we call them heating curves because these are following the process down from 920 down to when we have closed the dice and we are quenching out the heat and we open it up again, because we need to calculate for shrinking so we can do compensations. So we actually design the die bigger than the part or when it has cooled down. So in the simulation program we have heating, different heatings, and we have cooling water inside when we do the simulation, so we can have as correct as possible when we make the simulations. Of course, what we can see in the simulation, we can also see if we do as the simulation say in the reality. As we can see here, we have wrinkles, and of course we can see the wrinkles here. We see cracks, we can see the cracks, but we of course make the change before we can see that in the reality. But this is just to show how it works. And this is hot material. It's around 800. So if we have cracks, we have some kind of friction problems. And in cold forming, you can add on lubrication, some kind of oil. Here is it impossible because it will burn. So the only thing we can do here is make some coatings so we can lower the friction, make the surface much harder and stronger. Then we can get rid of the cracks. It's more problem with the wrinkles that you need to do in some other ways with the embossings operation or something. But that is what we play with in the simulation. The dies are built up like you can see here. This is a B pillar. We have in upper section 8 steel parts. And that is because we have a lot of cooling channels. So 8 parts, and maybe 12 parts. So we have quite a lot of parts, approximately 30 parts for each cavity. And all of these parts, I think this should come first, have holes, you can see here. Everywhere where this die are in contact with the heat material, you need to have cooling channels. So there is quite a lot of these cooling channels. And the forming process are different also to cold forming. You need to have some kind of controlled clearance with the upper and lower die. So when you make the forming, the die steels can't be in contact with the material. Of course it will be in contact, but you can't hold it when you go down. So this clearance is what you play with. If you have high clearance, much clearance, you have low friction, and if you go down with that one, more or less the material thickness, you have high friction, and that is what you control the wrinkles with. So this is quite different to cold forming. So we have a lot of hydraulic or gas springs inside, so we can control this clearance during the forming, and when we are in the bottom position, when the quenching starts, the press slide take over everything. Press forces, when you do the forming here, is maybe around 40-50 tons. It's not more, 40-50 tons, because this material is like a chewing gum when you make this forming. But when you make the quenching, then you add up to 500-600 tons, because as harder you can press, as fast you can take out the heat of the material. Yeah, we can take this one. Dissections, yes. This is what we use, Swedish type of material. Of course, if we produce to Germany, we have German material, but I show the Swedish one because I'm a Swede. So because of the volumes, depending on the volumes, high volumes need to have a little better material, medium volumes, yeah, and when we do verification dies or test dies for pre-production, we use some softer material. Plasma nitriding, PVD coating on the surface. That is to change the friction, and we do this in sections, as you can see here. We have divided this roof rail in 5 sections, and that is because if we have wear problem, and that we know we will have, because this have a much higher wear problems than compared to cold forming. So one of the things we do this for is we can take out one of the sections, we can re-mill it so we have the right tolerance again, put it back with the shim under, and then we can continue the production. One other thing is also for the manufacturing of the cooling channel. The smaller part you have, easier it is to make the cooling holes. And that is where we are coming into now. Cooling channels. Yeah. Everything need to go fast, forming operation, and so also for the cooling timing. We have a time window here in 10 seconds from 840 down to 400. We succeed with that, within 10 seconds, then we have a perfect part. And if you do the cooling channels better, as good as you can move this green dot line to the left, and then you can produce more parts per minute. This is what it looks like, B-pillar. We take in the water on one side, through all the dissections, and out again on the other side. And as fast as we can do it, the better quenching time we have. The die still looks like this. We drill the cooling holes from E5-axis machines from everywhere, of course in a good design way. We have 8 bar water pressure inside. We have a drop of water, 1.5 bar approximately. The flow is approximately 200 liters per minute in each cavity, so it's a lot of water running through here. We also do simulation of the water channels, and here is the same part, but we have designed the cooling channels in different ways. As you can see here, we have a really high flow of the water in the center. We have the same pressure in both. We have different pressure drop because of the different way to make the cooling channels. And we have different flow speeds. So it's really important. This one we have 0.5 meters per second compared to that one that we have 2 to 3 meters. So simulations, is really good. I mean, that have saved us a lot of times. This is what it can look like. You can see you have, if you compare to cold forming, we stop here, then we add all the cooling channels. So in one part it can be 10 meters, and then if you have 30 parts, I mean it's more or less than half a kilometer with cooling holes. So it takes a little bit longer time to make this one. Yeah, see if this works. This is one of the fastest way to produce. In production mode, we are down to 10 seconds here. We are transporting the part with transfer arms, and the thickness of this part is around 1.5 millimeters. Quenching time is 6-7 seconds. So this is one of the fastest way to produce it. But of course there are lines producing parts from 9-10 seconds, maybe up to 35-40 seconds. So depending on the needs you have, the volumes you have, you chose a line which can support it. But it's important with the dies. This is an AP&T dies, of course. So the temperature of the surface of these die steels is around 100 and it's going up to 120, down to 80, and 200. Yeah, it's going up now. So this is quite an interesting process. Yeah, this was what I had. I was ordered to don't speak more than 45 minutes.
Thank you.
So we have 8 minutes over for questions.
Yes. Питання, просимо.
Okay, Johan, thank you for this wonderful presentation. I have 2 questions. One is related to the life cycle of the die. So you mentioned that the wear is the main issue, and probably the thermo shocks for the die too. So what is approximately, let's say, life cycle for the forming die for the B pillar? Just
it's depending on the complexity of the geometry, of course, but you can say that where you have high wear, where you have high friction, we talk about the friction, then you maybe have a lifetime in 300,000-400,000 strokes.
Okay.
Then you can, and that includes the re-milling. You can re-mill the die maybe three times.
Okay.
And then you can, but of course, some areas where you don't have any friction at all, then you can run millions of parts. So
what are, for example, nowadays, let's say, the most efficient methods to, let's say, improve friction situation in this environment, 900 degrees, and improve, let's say, sliding lines, which are probably the major problem in the wear model?
What was the question? Yeah.
I mean, how to reduce the friction in this situation, or what are, let's say, future trends here?
Yeah, I understand. To reduce the friction, that is the discussion you have when you do the simulation. If you can do that together with the OEM in a good way, then you can point out we have areas, we have high friction, there you will have a problem. And that is up to the OEM to allow change according to lower down the friction or not. So the simulation tool is fantastic here. If someone asked me for 15 years about the simulation, I didn't believe it, actually. We have our old gray hair guys who make this without the simulation, but the simulation is better.
And the last question, you mentioned the spring back as an extremely important issue in this forming of high strength steels. Of course, even in a cold situation, this is more or less the major problem we are facing with. But anyway, in a cold situation, we mainly indicating the change of the E model, elastic model, as a function of accumulated strain. What is the major parameter you are following in a hot forming?
We don't have any spring back. It's none.
It's none.
No.
Even after the part is completely.
It's
super.
It's totally dead.
Oh.
Yeah, that is the fantastic things compared to cold forming. I mean, if you do a progressive die for 1000 megapascal material, you have a serious problem.
Wow.
Here we set it in the design. We don't have any spring back at all. Nothing.
So it's completely dead.
Completely dead.
Wow, super. Thank you.
I also have two questions. You integrate a number of technologies in your product, like materials, metallurgy, control, etc. And you also said you have competence, you keep competence in the company. How do you take care of the inflow of new knowledge? You have everything in the company, or you have some links with other groups outside the company?
We are a group, people, myself involved. We are out on the seminars and we are speaking everywhere, and we are out at the company's facilities. So, of course, we can see a lot of things there. But what we are doing, we have an R&D group. So we are doing a lot of research and development ourselves, because hot forming is quite new. When we start 2005 with the dice, it was 3 companies produced dice. This was Bentley, it was Gerstamp, and it was some more. That was Magna. That was all. So of course there are no groups, because everything was secret. No one tell anything to the other one. So if someone do a lot of mistakes, he didn't say anything about that. So all the other die makers need to do the same mistakes again, because of this quietness, so to say. So there are no groups. So you need to develop yourself. If that was the answer.
Yeah.
But maybe that will change, because there are more die companies starting up with this technology, and I think it will be the same as for cold forming later on.
So it is a kind of niche, you would say, but it's being filled up. You also imply it's the niche.
No. There is a lot of space for new players in this. As I told you one slide there, I mean the demands from the OEMs was here, and the capacity was here. So there is huge needs for this. That is what we can see.
Okay. This is the second question is. What is your market? What are your who are your major customers? We saw Volvo, but are you selling to all the car producers?
Yeah. Our competitors is not the OEMs, they are our customers. Our competitor is other press suppliers, press line suppliers. So I think there are 7 or 8 line manufacturers now in the world, but we are one of the top, number 1.
Thank you.
You spoke mainly about press hardening, but you also mentioned tailored rolled blanks. Did somebody already try to do, like press hardening of the tailored rolled blanks? This is done at the moment in the industry.
Tailor rolled, yes. There are tailor rolled UC-bore, tailor rolled bore steel. So yes, we are doing dies for that. Exactly what I show you, these B-pillar types of dies. So we are doing for General Motors right now a die with 4 different thicknesses.
All right. Are there any special issues about blank holder? Is it segmented, or how is it done?
Yeah, it is. The one side is flat and the other one is, So
okay. Thank you very much.
You need to think about it, of course, in the furnace. If you design the die in the wrong way, you can have these different thicknesses on the rollers, and then you have really big problems. So there is things in the process to think about.
Okay, thank you.
Še kakšno vprašanje? Imamo še nekaj časa.
I have two questions. First one is, you mentioned that the part after the quenching is a little smaller, so you have to build a bigger die. Is that true?
It shrink.
Yeah. So do you have any problem how to take out the part because the die is bigger? So it doesn't stuck in?
No. As soon we have made the forming, we lift it out, because when we lift it out, the die with the lifters, then the part have the same shape. But and the part is around 200 Celsius. And then from this 200 Celsius down to 20, there is the shrink. So it's you can't put it back again.
Okay. And the second question is, do you have any problem with shearing or punching this quenched material?
You mean to punch a hole, or?
Yeah, like for example, yes.
Of course, yeah, there is, of course, but to punch a hole, no, there is no. I mean, there is ways to do that. If you have the right size, you can't punch a hole which is 6-7 millimeters. That can be a problem, but 10-12 is not any problem. And there are companies, Fiat for example, they have 2 big lines, mechanical press lines. They cut everything of the parts in 4 or 5 operations in that line in hard condition. So there is different ways. You can make laser cutting, or you can make hard cutting in cold condition.
Okay, thank you.
Še kakšno vprašanje?
Sorry, 2.5 minutes. Overtime.
Overtime?
Yeah, 2.5.
Really?
Yeah.
Then we have to finish. Thank you again.
Thank you.